Okay, lecture 14. Hopefully this will be your last lecture. So we're going to study the particles and particulate matter testing methods of different kinds, and sterile product package integrity testing methods, stability and sterility testing method, and storage and distribution conditions. We'll talk about those. Okay. Number one, particles and particulate matter testing. So we talked about the importance of not having particles or particulates in your final injectable drug products, right? So if they are there, of course, you can jeopardize the health condition of the patients, of course. So according to the USP, US Pharmacopoeia, particulate matter in injections and parenteral infusions consist of mobile, undissolved particles, things that are not mixed well with water, of course. And then other than gas bubbles, gas bubbles are not considered as particles, okay? And then unintentionally present in the solutions, of course, you do not intentionally put those particles in there. So those are the particle matters that can be existing in your final product. Normally, particles are visible through your naked eyes if they have size about 30 to 20 micron size. They are pretty significant. Okay, so if those particles are injected with your drug to patient, if they are injected intravenously, they will give a big problem because they may end up into the lung and give a big inflammation in the lung area, because your immune system will recognize that as a foreign matter trying to fight up, or blockage of your blood vessel may take place. We call that emboli or embolism. Okay, so those are not good, because if you have a blood vessel blockage, that tissue may die because of lack of oxygen and everything. But so that's not good. Okay, so the presence of foreign matter in injectable drugs, that presents a very difficult challenge. You should not have it, but there are so many different sources where those can come and mixed up with your final product. Okay. So visual inspection is one way of getting rid of those, counting as them defect and trying to remove those. But those sometimes work, those may not work sometimes. So you may need to have some different methods if the problem persists. Okay. In an animal study, when they injected a drug with large particles, they see what happens to the animals. If you inject large particles that have size about 20 micron or bigger, the diameter size, and mostly they end up in the lung, because that is the tissue organ area where a lot of bloods will end up for, of course, gas exchange, right? And if it's a small particles, they can go into different organ tissues like liver, spleen, or kidney. But wherever they end up, they will do bad damages to the organs. So you definitely do not want to have particles in your injectable drugs. And the smallest capillary blood vessels have about 7 micron diameter. Okay, so if you have any small particle in your drug that are same or above that 7 micron size, again, you can cause the blockage of those capillary blood vessels. So that causes embolism or emboli, which is not good, and the tissue will die from that area. So then where do they come from, those particles? They can come from anything, any sources that come in contact with a parenteral solution, your formulation, your drug. Okay, so they are contaminants you should not have. Okay, so examples are undissolved chemicals. If they are not fully dissolved, they could come when you make your solution formulation. They may come from the chemicals, or packaging components like glass pieces or plastics or rubber closure systems or debris and things like that, or could be environmental contamination like particles that are floating in the air, or processing equipment. There may be some things coming from maybe tubings or whatever the components you use, fibers or people, skin flakes or hair, or possible things. Okay. All parenteral product contains some level of particulate matter contaminants, as it is impossible to prepare product completely free of them. Okay, but the question is how much is there and how much is allowed. Okay, so besides, of course, visual inspection of all your drug vials, okay, there are a couple of methods that you can use to do the testing in more detail. So according to US Pharmacopoeia, particular matter testing in injectable drugs, they recommend these two methods. Number one method is called light obstruction or obscuration particle count test. Light obstruction particle count test. So you have to have a special device called HIAC, HIAC. That stands for high accuracy liquid counter. Okay, high accuracy liquid counter. So it looks like this. There's a light bulb, tungsten light shining the bright light, and then your drug will go through the area, so where light will go through, and there's a sensor on the other side. So if there's any particle going through, and then that they will maybe absorb light or deflect the light, so the last light will be absorbed. So the machine will sense that the presence or absence of the particulate floating in the liquid. Okay, so it's very accurate method. The counters are calibrated using dispersion of spherical particles of known sizes. So there may be some particle standard that you can use. They have 10 to 25 micron sizes. Okay, and see if this machine can really measure those. And then after that, after you establish the baseline, you can do the counting on your drug. So it's very efficient. Like I said, you can measure about 4,000 particles per second. So very highly automated method. Understand? Light obscuration particle count test is one method. Another method is a little more manual, because you have to use a microscope. So in the field of view, manually you can view the area and count those. So like here, maybe the sample can be added on a filter paper like this, and then you take a look at the field of view of the filter paper and see how many particles you can count. Okay, we call it the microscopic particle count test. So it provides both quantitative and qualitative. What's the difference? Quantitative, you can count the number of particles you can find. Qualitative, you can understand what kind of particle they are. Are they rubber, pieces, or solid matters, or hairlines, or what the fibers. You can identify the nature of those. Okay. So particles larger than 10 microns can be counted and sized and described what they are in terms of their shape, terms, and nature, where they are coming from. Do they look like cotton fibers, or glass pieces, or metal pieces, or etc. Okay, so all operations and manipulation must be performed under a certified laminar flow hood. Makes sense, right? Because particles should not come from the observer or operator, of course, and then the microscope operation itself. So you have to do it under the very clean room environment, like a biosafety hood that provides the class 100 environment. Okay. Use of non-powdered glass is absolutely required, because you don't want to generate those particles through your glove. Okay, so that's another method. So microscopic particle count test. It's manually counting the particles under the microscope. The other one was what? Light obscuration particle count test. Two major methods to count the particles or particulates in your product. And how about biopharmaceuticals, injectable drugs? And what happens if you have particles in biopharmaceutical drugs? Normally, the small particles can affect mostly the protein products, so they can get aggregated. Okay? So if they are aggregated, they just in a big, large garbage clumps, then they can cause immune responses if they're injected into the human patients. So that's not good. Instead of giving the efficacy, you can harm the patients. So when proteins form aggregates, they can form large particles the size about 1 millimeter, that's the largest, maybe, and small as like 1 nanometer sizes, and they can come in different shape, and so it's difficult to identify and count those protein aggregates. Okay? And so during the formulation development of the biological product, soluble aggregates are being measured normally by size excursion chromatography, because excursion chromatography can separate out the things based on the sizes. So large aggregates can come out first, right? And your small drug can come out later. So after collecting those, you can measure the size of those. And if particular matters are observed prior to injection, package inserts recommend injection or use of syringe or inline filters to remove them. What it means is, if you cannot get rid of them, you have to recommend that they should be removed before they are used. And how do you remove them? Maybe you can use a filter. Maybe you can have a filter attached to in your syringe line, so the administrator can remove those. Or if possible, of course, you can reject that product batch, of course, so they should not be released. Okay, that's what it means. Now let's talk about sterile product package integrity testing. So we understand different packaging materials you use for your product, right? Primary packaging material, secondary packaging material. So you need to test the integrity of those packaging materials and see if they are still intact, they are not leaking, or they are not damaged, right? So we consider those package integrity testing. Okay, so especially container closure integrity is very important to keep your product safe and stable. So you need to make sure that the measure of a primary package has the ability to keep the product in and keep potential microbial, particulate, and chemical contaminants out. So our product should be kept safe, but any foreign matter should be kept outside. That's what it means. That's the function of the primary container. And there are various types of tests that are out there. We'll take a look at some of those testing methods to make sure the integrity is good. Simple tests are called bubble test. So it's not bubble point test that you use for your filter. It's called bubble test, right? So as you can see this from this picture, bubble formation is observed from a package that is immersed in water with a vacuum or pressure is applied. So it's kind of destructive testing. So if your product is there and it's hooked up with pressurized air or gas completely, then there shouldn't be any leakage. If there's a leakage, you can see the formation of a bubble. So that's how it works. Simple test, bubble test. And the next test is called dye or liquid tracer test. So this picture shows a lot again. So you can immerse the testing package in a solution of either dye or other chemical tracer, and that allows a time for liquid to migrate from the solution into the packaging material and see if it goes in. If it goes in, of course, it failed, right? So it's a kind of destructive testing. So it's inexpensive and simple method, but it's a very good test as well. Okay, so bubble point and dye liquid tracer test. And another test is non-destructible test. It's called the electrical conductivity test. So you see the vial that's sealed with the rubber stopper and then crimp, right? And then if that vial is leaking the liquid content outside, the conductivity will change when there's electric current is measured. Okay, that's how this conductivity test works. So it's also called as high voltage leak detection test, okay, HVLD test. So if liquid is leaking through this plastic glass or any other primer container, you will see a change of conductivity from that area. So that's how this testing works. Okay. So this is considered as a non-destructive testing because this drug can be still used if it passes, of course. Another test is called frequency modulation spectroscopy. Okay, again, this is a rapid non-destructive test, another kind of non-destructive testing. It's suitable for monitoring oxygen and water concentration as well as evacuated pressure level in the headspace of the sterile product container. So how does that work? So this is your vial, drug vial, right? You are shining the laser light on the head space of the drug. So your drug is located at the bottom and it's sealed. The head space area, your laser light is going through. So at the other side there's a sensor that measures the light absorption. So if there's any leakage, you can detect that through the change of the laser light. So the laser light can monitor the oxygen concentration or water concentration on the head space. Okay, so laser light absorbed is proportional to the water vapor concentration. So if it's leaking, of course, there's going to be much less water vapor. That's how you can detect the leakage of your primary container.